All right. Hi, everyone, and welcome back to Product Training with Blue Triangle. Today, we're going to talk about function tracing and how it allows you to see what's causing slowness on your website. Many of you probably know that site performance plays a big role in determining your SEO. And Google's algorithm for SEO puts heavy weight on the speed of the time to interactive metric. So today we're going to dive into how we can improve time to interactive using function tracing in Blue Triangle. Before we get started, if you've joined us before, you know we'll post a recorded version of our session today in the Blue Triangle Help Center. So if you'd like to share this, you can do that at help.bluetriangle.com. Also, we'll save time at the end of the session for questions. So feel free to ask those questions using the tab to the right of your screen, and we'll be happy to go through those with you. Okay, so let me introduce our training manager, Christina Ravensbergen, who's going to be leading the session today. Christina has been hard at work over the last several months putting together our new Blue Triangle certification program, and I heard she was just working on the section about function tracing. So I'm really happy I was able to get her time today for this, and I think we're all in for a really great session. So Christina, now we'll pass it over to you.
All right, thanks, Mark. And hi, everyone. I am going to be walking you through today not only how to use function tracing in the Blue Triangle portal, which I will get to towards the end of the session, but I'm going to go more in depth about what it takes to optimize TTI on your website, specifically as that relates to JavaScript. So let me go ahead and get started here. First of all, what is function tracing? Function tracing is a tool that Blue Triangle developed. It allows you to trace how long JavaScript functions remain in the call stack of the browser. So I'm going to be explaining a lot of the terms that I go through here and sort of making it really, really clear as to what is going on the page that causes JavaScript to run for a long time and that ultimately affects time to interactive. So functions that remain on the stack for 50 milliseconds or longer, so that's 0.05 seconds, are considered long tasks by Google in their performance calculations for time to interactive. So Blue Triangle calculates TTI the exact same way as Google, and our function tracing correlates sort of these long tasks with where they load on the page and execute on the page and when time to interactive actually occurs on the page. And function tracing then allows you to see, and it explains gaps in content download on a page, and it shows how those functions that might be preventing content from downloading also fit into the content download schema. So the next slide here is just an illustration of a function tracing measurement that we took for Amazon's homepage. So this is showing all of the functions loading on the page that took longer than 5 milliseconds. And you can see there are a couple of really long ones. This function Q from the file name default lasted for 3.5 seconds on the page. What this means is that the 3.5 seconds went into the call stack and then it called a bunch of other functions that executed one at a time. So while this might not totally block content, it can block things like user interaction, content download, depending on how it's loading and where it's loading. And you can kind of see in our waterfall graph as well, all of our performance metrics correlated with the functions executing. So we can see that almost everything at this point on the page has occurred. Onload has already occurred, but time to interactive doesn't occur until much later in the page. And that's likely due to the requirements that Google made for functions to execute in a minimum amount of time. Anything that's color-coded red here is considered a long task. So those would be functions that are lasting longer, or 50 milliseconds or longer. So 3.5 is well over 0.05 seconds. And you can see that even short little functions like this are considered long tasks in terms of the definition that Google gives for time to interactive. So function tracing in the context of Google Lighthouse scores. Function tracing allows better optimization of different performance metrics related to Google Lighthouse. So not only does it optimize or help you optimize time to interactive, it also gives you insight into First Contentful Paint, first CPU idle, and estimated input latency. Those are all sort of metrics that Google Lighthouse uses for their performance rating in order to give you better or worse SEO as a result. The thing with function tracing is that it allows you to see which functions stay on the call stack for a long time, especially early in the page. Functions that stay on the call stack early in the page for a long time can affect all of these metrics, including first contentful paint, which is how early a user will see any content that has loaded on your page. Estimated input latency could be something like a user clicks on a button and nothing happens for 2 seconds because a function is running. So function tracing helps you to see sort of what's going on the page and helps you diagnose when there are issues. In order to sort of give you a better idea of what it takes to optimize time to interactive, it's helpful to know how Google is calculating and how we are calculating time to interactive to give you more insight into what is going on the page. So in order to read this chart over here, you have to know that these are network requests. So this would be content, pieces of content downloading. And it's kind of like the waterfall diagram that we have in Blue Triangle. Underneath that, in this chart, it's correlated to navigation times. So we have navigation start, and then we have the lower bound, which is a condition for time to interactive to occur. Same with DCL end. So this is DOM content loaded end time, and then time to interactive occurring right here. So this is over time, what is happening during the page load and the conditions that need to be met. So the 3 specific conditions that have to happen are that the lower bound or DOM content loaded has to have occurred. So this can be either first contentful paint or DOM content loaded. It depends on your definition, but DOM content loaded is generally considered the event that is the lower bound for this TTI to be able to occur after that point. After DOM content loaded has happened, you also have to have a network quiet sub window where no more than 2 resources are downloading at any given time. So you can see that that network subquiet window of greater than or equal to 5 seconds doesn't actually happen until this point in the page load. So we can see that anytime before that point, more than 2 resources were downloading at any given time. The last and probably the most important condition is the quiescent window. So quiescent window is defined by JavaScript. And in that window, no blocking task of greater than or equal to 50 milliseconds of duration can happen. So tasks that are longer than 50 milliseconds are those long tasks, what we call long tasks. And those are what we color-coded red in our waterfall. If any of those occur during the network subquiet window and prevent a quiescent window, of during that network subquiet window time to interactive can occur. But once both of these conditions are fully met, time to interactive is put at the beginning of the quiescent window. So even though there are multiple network requests happening here, because the quiescent window happened while the network subquiet window was happening, time to interactive occurs at the beginning of the quiescent window. So I know it's a little bit complicated, but rest assured we're calculating this correctly in our portal. We have algorithms in place to make sure that all of that is being calculated correctly, but it can be useful to know what's going on, right? So TTI is occurring at the beginning of the quiescent window, and that is defined by network activity and how long JavaScript is taking to run on your page. Keep in mind also that a long task, any task that is greater than 50 milliseconds, regardless of whether it gets executed right away, it's just how long it remains in the call stack, basically. So this isn't necessarily execution time. It could just be how long the task remains on the call stack. So I'm going to explain a little bit about JavaScript as a result of this. The best way to optimize for TTI is to optimize JavaScript and network activity. So I think network activity optimization, that is a discussion for another time. There's a lot that goes into that. But today I'm going to be covering a little bit more of the JavaScript side of this and trying to help you understand sort of what's going on in the background. So in order to optimize JavaScript, you kind of have to understand how it's working. In order to optimize how long tasks are taking, you have to understand why they're taking that long and how JavaScript really works on the page. JavaScript is a programming language that adds a lot of dynamism to web pages. It's honestly the backbone of the modern web. Most web pages today could not exist without JavaScript's functionality. And so it's even more crucial to understand how it's working, right? So JavaScript as a language is single-threaded, non-blocking, concurrent, and asynchronous. Single-threaded means that it can only handle one execution at a time. Non-blocking means that when it's written properly, it won't block other tasks from occurring. So when it's written properly, if you interact with a page, that will get processed more quickly. If it's written properly, when you download content, that JavaScript won't block the page either. Concurrent also means that JavaScript has access to APIs that allow it to do multiple things at any given time. So it's not only going to be processing one thing, it will only execute one thing at a time, but there's going to be some features in place that allows it to accomplish multiple things over a period of time. And asynchronicity sort of refers to that, where JavaScript doesn't necessarily have to execute things in the order that it's read. So the browser reads everything in JavaScript on a single thread, so one at a time, but it executes things asynchronously. And it does that with some features that I'll get into in a minute here. So there are three main parts to JavaScript and how it works. And the first one is the call stack. And this is the most important part of JavaScript execution. This is where JavaScript executes, basically. Call stack contains all the functions that get read, and they get executed one by one out of the call stack. There's also a callback queue, and the callback queue is where asynchronous code goes to wait until it can be called back into the call stack to execute. And what links these two is the event loop. So things that get pushed from the call stack to wait in the callback queue, that's done by the event loop. And then the callback queue has the callbacks pushed back onto the call stack by the event loop. So the three main parts sort of make JavaScript work in the browser. To better understand this JavaScript call stack, you have to know that there are a couple of key features of this. The stack is the order that JavaScript runs in the browser, like I said. And one thread, JavaScript is single-threaded, remember, means that there's only one execution stack, which means that there's only one call at a time. Some calls can wait while other code runs and then it executes. That refers to JavaScript's asynchronicity. So JavaScript is asynchronous, even though it is single-threaded. And the reason that can happen is that browser APIs allow asynchronous callbacks. These callbacks contain pieces of JavaScript code that wait for execution via the browser APIs. But the problem is that no JavaScript code can be added to the call stack from like the callback queue, for instance, until the end of the current scope or is reached. What that means is that the call stack has to be empty before more code outside of the scope can be added. So that includes JavaScript that is in the callback queue. To give you an example of this, consider us having a bit of JavaScript code on a web page. And this is just very simple code that's going to be read sort of line by line and then executed when a function call occurs. So we have this execution stack, which is the JavaScript call stack, basically. And what happens is we're going to have the main context of the page, which contains these functions. And then the browser is going to read through the code that we have and execute it as things get called. So all of these functions at the top here are sort of storage. It's just naming the functions. It's not actually calling any of them yet until you get down to this print cube function call. Print cube function call is referring to this print cube function. So inside of the print cube function, this code gets read. And you see var cubed gets defined as a function call, cubec. So cubec is going to get added onto the execution stack. And then the browser is going to read the function cubec and execute it. Whenever there's a return statement, that function will get pushed off the call stack. So once that function gets pushed off, the browser goes back to the original scope of print cube and reads the next piece of code. So that's console.log cubed. So the console log happens and print cube or console.log gets pushed onto the call stack. That's another piece of code execution that executes. So the console.log will print whatever the result of that function was. Print cube then gets pushed off the call stack as well. And then finally, main leaves the call stack. So you can sort of tell that things get read in order. Not necessarily everything gets pushed onto the call stack, right? So we had this function at the top, function add, that never went into the execution stack because it was never called in the scope. So this is something that you can kind of keep in mind when you're optimizing your code as well. You want to get rid of functions that are never actually used in your code on a page, because it helps lower the file size for JavaScript that gets delivered, and it reduces processing time. When the browser has to read this kind of function, it has to store it somewhere, right? So it knows that it's there, it takes up some processing power, and it basically consumes browser resources that don't need to be consumed. When you optimize your JavaScript to only include essential functions, you're doing the browser a real favor in helping it to process things faster. In addition to just the call stack, JavaScript uses a couple of browser APIs, like I mentioned. So for concurrency and asynchronous execution of code, JavaScript uses the event loop and callback queue. So we went through this a little bit before, but there are also a couple of web APIs that allow JavaScript to use the callback queue in a specific way. So the document, the DOM, basically is a web API that JavaScript uses. Same with AJAX or XML HTTP requests. So those are sort of asynchronous callbacks. And then set timeout is another asynchronous callback that utilizes the timer that gets set in the browser API. And then it uses the event loop and callback queue to queue the callback after the timer runs out. So for example, we have this new piece of JavaScript code here. And you can see we still have the JavaScript call stack, but now we've added the event loop and the callback queue. And I'm going to go through another example with this in a minute, but understanding what is going on with the callback queue can be pretty essential too. When web APIs are done running, events and callbacks get pushed to the task or callback queue. So this is also called the callback queue, task callback queue. And once the browser APIs like set timeout are finished, the callback will get added to the callback queue. And then once this JavaScript call stack empties, the event loop will push whatever is at the top or the front of the callback queue onto the JavaScript stack. So that's this next point. The JavaScript call stack has to be empty before callbacks can be added to the call stack. And then the reason behind this, that the browser doesn't add callbacks onto the top of the stack right away, is that the call stack will process things at the top of the call stack. You don't want to add callbacks that aren't high priority to the top of the call stack if it doesn't make sense to the page. The browser single threaded, right? So doing it this way prevents concurrency issues where there are issues with logic and how things are running. So this is the example that I had just put in the previous slide in a little bit of a smaller font, where we have a new little set of JavaScript code, the call stack and the callback queue with the event loop, sort of synchronizing everything in between. So just to go through this, we have the console.log here of hello. We have a set timeout function, which is utilizing that browser API that requires a callback and then a timer. So here our timer is 2.5 seconds or 2,500 milliseconds. And then we have another console log, which is there. So you can see the first thing that happens is we have our main context of the page again. And then we also have the console.log for hello. So that will get logged and leave the stack. The next step is set timeout gets read and goes into the call stack. But set timeout uses a browser API. So we have the callback here, which is a function, which contains console.log with theme at the end, and then the delay, which is 2,500 milliseconds. So that will actually get pushed into the browser API for set timeout, which includes that callback and that 2,500 millisecond delay. Meanwhile, the browser just moves on to the next piece of code. So console.log there will get added to the call stack while the browser API is waiting for this 2,500 milliseconds, and it will finish while the browser is still waiting on this 2,500 millisecond delay. Usually console.log does not take much time at all. So this will wait long after the JavaScript call stack is empty. And you'll notice the event loop is sort of processing all of this, but there's nothing in the callback queue, right? So it won't get added to the call stack right away. It has to wait for this 2,500 millisecond delay. Then it gets added to the callback queue. So this callback is now in the callback queue. and the event loop can then add it to the JavaScript call stack. So we had gotten to the end of the piece of code, main left the page, so the call stack was empty, the callback got added to the callback queue, and then the event loop pushed it onto the call stack. So the event loop determines when to push tasks in the callback queue onto the stack. It waits until the call stack is empty to move tasks from the callback queue to the call stack. And the event loop occurs on the main thread of the page. This is really, really important. Callbacks, like I have here, which I now notice it says it's misspelled. That's because of the picture of text. But I added just a couple of examples. Like if you have an on-click event, that will be registered as a callback typically in the browser. So imagine that you had a function that there was a callback and then another function got added onto the stack. The callback got added into the callback queue, but while a user was waiting for all of this to process, they clicked something twice. Maybe it was the same button that they clicked twice, and those both got added to the callback queue. Unfortunately, this function is taking a really long time to run. And what that means is that it's never actually leaving the call stack. Because it's never leaving the call stack, main can never clear the call stack either. And these callbacks won't actually get added to the call stack one at a time until this call stack is clear. So you can kind of see how a long running function might cause pretty significant issues on the page, where if this never leaves, these clicks by your user will never get processed. So to sort of understand this a little bit better, I wanted to give you an example of the main thread of the page. The main thread is basically where the event loop operates. And it doesn't only handle user interactions in JavaScript, it handles user interactions, it handles animations, style calculations, page layout, paint and render, and JavaScript execution as well. So there's a lot that this main thread of the page is handling. And I have a pretty hard to read illustration here of how that works. We have almost all JavaScript functions going into the task queue. There are some micro tasks that might get queued somewhere else and things that affect animation and that kind of thing. But basically what's happening is the event loop is running really, really fast here. It runs faster than tasks can get queued or render refresh can happen. Tasks are queued at the rate that this sort of gate opens. So imagine that this gate opens whenever a task is added or as quickly as a task can be added. Additionally, there's also this render gate. So this gate will open and allow the ball through at the browser refresh rate, which is typically 60 hertz. So that's about 16.6 milliseconds if we're getting technical. And we also have style, layout, and paint here, which are sort of the animation styles and rendering that happen for a user to see your page. Now let's explore what happens when a task gets added and the gate opens. The event loop will go and try to complete that task. Once it completes that task, it'll go around again and another task gets added, so the gate remains open. And you notice that while we're doing this, the gate for the animation styles and rendering opens. So the event loop goes around, tries to complete the next task. If this task never finishes, the event loop will never get around to doing the animation styles and rendering for the page. So the style, layout, and paint over here, these are all things that happen in the browser at a given rate, but they don't necessarily happen every single time. And tasks can actually block style, layout, and paint from happening in the browser. So this is why optimizing JavaScript is really, really important. So I'm going to switch over to my browser here and take you through a little bit of function tracing, and hopefully my explanation of how JavaScript works and why it's really important to optimize it in your page is helpful to you. Right now I'm looking at the last 7 days of data, just about, and I'm looking at a measurement that we set up for the Amazon homepage. So if you go to Amazon.com, you'll get results similar to these. We have time to interactive and time to DOM content loaded trended in this graph. And you can tell that there are some times when time to interactive gets pretty high compared to others. This time it was overnight. Over here, it automatically selected the highest point on the graph. So you can actually see time to interactive out of the measurements that we took was 5.99 seconds. So almost 6 seconds until time to interactive in a synthetic measurement. So that's not fantastic. When we click on this graph, we can actually see what the scatter plot looks like that led to these results. So I have time to interactive selected here as the displayed metric for the scatter plot here. And we can actually see that there are, on average, things tend to load, or time to interactive happens to occur in less than 10 seconds the majority of the time. So that's in line with the average over the week, but we do have a couple of outliers here. So if I click on this point, which is a definite outlier, it got a 200 response code, so everything looks good, but time to interactive didn't occur for 23 seconds. If I scroll down further in the graph, you can actually see the details of the page load, but not only can we see like resource data and the exact domains and files that were loaded, we can also look at function tracing is here as a selectable page that you can view the exact waterfall of functions that we're loading, how long they took to load, what file they loaded from, and you can kind of see their dependencies also. So for instance, this default file with this anonymous function would have called this function, and then the next function would be called. So you can kind of see where the dependencies lie. If we remember what the call stack looks like, the main function stays on the call stack for the entire time that everything in its scope is executing. So that's kind of what's happening with some of the longer functions here, right? You have a long function go in and then the rest of the resources execute. This doesn't necessarily mean that other things can't happen in between, because as we saw in that event loop animation, when you have a task, it will complete the task at the top of the call stack that gets added. Actually, let me switch back to that PowerPoint and just give you an example. So if we go back to when the task queue is full, this task would be like at the bottom of the callback or call stack. Call stack, execution stack, and task queue are all sort of interchangeable terms here. If you have this task at the bottom of the call stack, it's not going to be executed for a while, but it doesn't necessarily block render from happening because it's still on the stack, right? It only blocks when the event loop goes to execute the exact task that's happening here. So only tasks that are currently being executed can prevent style, layout, and paint from happening. That being said, this kind of involvement of a particular function can be suspicious and should be taken note of, because these functions are taking well over 2 seconds to execute for each of them. Most JavaScript functions will execute in very, very little time. In fact, we have to have a limit put in place as for the minimum duration of a function that you want to track, because most functions aren't going to be problematic like this on a page, right? They're not going to take a whole second or half a second to run. So we can see, for instance, here, this first default function takes over 0.6 seconds to run. But you can see sort of how long these functions are taking. The blue ones here in the function tracing view are going to be ones that take less than 50 milliseconds, or 50 milliseconds, yes, so less than 0.05 seconds. So for instance, this one is taking only 0.04 seconds, hence it's not a long task. The one right above it is taking 0.116 seconds, so 116 milliseconds. It's a long task, according to the time to interactive definition. If I switch over to function tracing and object level detail, we can actually see the individual files that are loading on the page correlated with the JavaScript functions that are happening here. So it's possible that more JavaScript was happening earlier in the page, but they would have been really fast functions. And not only that, as you get down further in the page, you can see that there are gaps sort of in the content loading. So the gap between this content and this piece of content can sort of be explained by the JavaScript that's executing in between. As you tend to get later in the page load, more JavaScript tends to happen and execute on the page. And this may or may not cause a delay in time to interactive. So time to interactive, we see, didn't actually occur until out here. And that's because a lot of the functions that are executing at this point in the page load are taking longer than 50 milliseconds. So for instance, this is 233 milliseconds. Time to interactive won't occur until that is over. 233 milliseconds might not seem like a big delay, but you have to keep in mind that when a user interacts with the page and they click something, they want that response to be quick. They want their scrolling to be smooth. And the sort of style, layout, and paint that I was talking about before happens every 16.6 milliseconds. A perceptible delay for a user, this is what Google determined. It had to be less than 50 milliseconds. So that's why a long task is defined as 50 milliseconds by Google. It causes user input delay, basically, and prevents them from having the smoothest experience of your page possible. Once you determine sort of what the unoptimized functions are on your page, and you can actually do that by looking at a graphical view as well. So I switched back to just the function tracing waterfall, but you can see it in a graph format as well. And I can sort by duration here, where I can see what functions are taking the longest to load and from what file. We actually have a couple of our customers right now who are setting up function tracing measurements in Synthetic using unobfuscated JavaScript files. And that will tell them exactly what functions and the names of the functions where these unoptimized execution times are occurring. We can see this on a page-by-page basis, but we can also look at it at an aggregate level as well. So this is that we do have aggregate level information on this as well. So this is function tracing and object level detail, but it's looking at an entire week's worth of time instead of just one measurement at a time. So not only can you see problematic measurements where, so if I scroll back up here, we can see that this was kind of an outlier, but I would have to click on a bunch of these measurements in order to get a more holistic view of what's going on with the page on a regular basis. The aggregate waterfall sort of gets around that problem by showing you an aggregate view of how functions are loading and executing on the page. So you can see which ones regularly take longer than 50 milliseconds, what they're called, what files they belong to, that kind of thing, and how many times we measured them loading. So a function might not happen every time a page loads. This one, the function count is 82. So we know that over the week, we measured at least 82 instances of this function versus 223 for this one. So it will just depend on the different circumstances of the page load. This function name T, file name default, function count was over 1700. And we can see that on average, it's taking 344 milliseconds to load every single time. So there's a lot of detail that you can get from this. There's a lot of information about which functions you can then go and try to optimize. And JavaScript optimization, and unfortunately I didn't make a slide for this for you to take a screenshot. So JavaScript optimization relies on things like efficient JavaScript code writing. So that includes obfuscation, delivery, and compression of JavaScript files. And it also relies on making functions as readable as possible by the browser. But more than that, it depends on delivering smaller files, less processing intensive files. So there are optimization techniques like tree shaking and code splitting, route splitting, chunking, that kind of thing, that allow you to better control what JavaScript is executing on your page, when it is executing, and seeing the dependencies of the different JavaScript files. So that's pretty much all I have for you today about how to use function tracing. I do want to show you really quickly how you can set up a function tracing measurement that will give you this kind of data. So I'm under the creation of a single page monitor here, and you can see that I've gone through most of the stages of this, and I'm on stage 6, which is where you enable function tracing for a single page browser monitor. Here you just turn function tracing to on. For function tracing collection percent, this is going to depend on your contract data and how many function tracing measurements you've enabled in your contract. A lot of the time we see just 20% across most of the measurements, but this is for our demo data, so we have it at 100. The function tracing minimum function duration is what I was talking about as for how or which functions that we will even capture based on how quickly they're running on the page. In this case, it means that anything that's 5 milliseconds or less than 5 milliseconds, we won't even bother capturing just because it's happening so quickly. It's not really going to affect time to interactive. Same with the function tracing maximum function count. For each function tracing measurement that we run, we'll collect, in this case, the top 100 slowest functions on the page. So this minimum might not even come into effect. Maybe the top 100 slowest functions all take longer than 200 milliseconds to load. It's just going to depend on your page and how much JavaScript is loading there. But you can see the usage details about how much you've used of your measurements underneath when you click that open. I just wanted to show you that this is how you would enable function tracing for one of your single page measurements. And I think that's it. Do you guys have any questions?
All right. Awesome. Thanks, Christina. Okay. With that, guys, we appreciate your time. And if you do have any questions, we're happy to speak with you offline. So as always, feel free to reach out to your customer success manager with any questions, or you can reach us here anytime in support via the Help Center at help.bluetriangle.com, or you can also email us at support@bluetriangle.com. And for more information about Blue Triangle product training, how to watch previous sessions, how to register for upcoming ones, definitely visit our Help Center. Again, that's help.bluetriangle.com. And when you're there, just click the big button for product training. All right, guys, that's all we have for you today. Thanks again for your time, and we hope to see you in our next session. Have a great day.